Alright, hey, welcome back to part 5 on retro computing. Today we're going to get out of the box. So, normally CPU is running, it's reading memory, it's modifying memory and registers, but it's all kind of happening inside the CPU. It's nice to be able to get outside of the CPU and interact with the outside world. So, since I'm using a simulated CPU, the outside world is also simulated for now, but we can change that later. But let's take a look at peripherals. So bitsaver.org has, among other things, the PDP-11 Peripherals Handbook. This is a really useful guide if you're trying to start playing around with some of these devices. In particular, the Appendix A. So the UNIBUS was the bus that was used to interact with I/O subsystems. And basically on the PDP everything is memory mapped, so there's certain memory addresses that instead of just being a plain old location in memory, we're actually connected to physical devices. And the ones we're going to play with in this video are the console terminal, also called printer and keyboard. So the consoles generally didn't have visual displays, they were large teletype machines, or deck writers were popular on the PDPs. So you would type, and as you typed, a print head would just print out what you were typing, and when something came in to be displayed, it didn't display on a graphical screen, it printed on the console, and you'd have a hard copy of everything you did in the end. This is called printer, and keyboard, this is basically the output, and this is the input side. So let's go ahead and fire up our tools. So I'll go into a work area, I'll start the emulator, make this window a little smaller because it's mostly there just for fun. And first thing we want to do is create a virtual device. So this device was called a DL11, and it would be a teletype writer type device physically connected to the box that this panel was sitting in. But on the simulator we can mimic this by saying set console telnet equals, and we can just pick a port number like 1250. And now if I open a telnet session and I say something like telnet localhost 1250, this is playing the part of that physical console. And if I just step my simulator once, I'll get a welcome message from the simulator saying I'm connected now to the console. So let's look at these registers. We're going to be mainly interested in these data registers. So the printer data is 177566. So let me set up a infinite loop here at location 1000. We'll just have a branch to 1000, and I'll put a 1000 in my program counter. So if I run this now, you can see I'm just sitting at address 1000, and if I say continue, it'll just stay at 1000. So let me drop something into this register. So our printer data is 566, so deposit into 566, and let's put in a 101. That's the ASCII code for an uppercase A. And now if I let my simulator continue, I get the letter A up here. And if I pause that and I put a 102 into that same register and I continue, I get the letter B. And if I put in a 103 and continue, I get the letter C. So I can output from the simulator to this connected console by just depositing into this register this memory location 566, which is listed as printer data. I can also do input. So let me do a control right bracket to get back to my telnet prompt. Let me say mode character, which instead of waiting for me to type a whole line before sending something, will send characters one at a time. And I want to look at this keyboard data register, which is 562. So if I look at location 562 with an examine, it's got a 0. and it's still a 0. But if I come up here and I'm going to hit, I don't know, I'll hit a space bar. And then if I come down here and I examine that location, it's no longer 0, it's 40. And 40 octal, 4 times 8 is 32, that's the ASCII code for a space bar. And now if I come up here and I hit the letter A, and then look at my simulator and see what this register contains, it should have the ASCII code for A, which is 101 octal. There we go. So we can receive characters from the console by reading this location, and we can transmit characters from the console by writing to this location. Alright, so we should be able to do that in code. So let's make a console program. So we'll play with console I/O. We're always going to use absolute addressing so we can locate things in memory exactly. We'll just start at location 1000. We'll put a label there so we can tell the compiler that that's where we want to begin. And first thing I'm going to do is set up my stack pointer, just with, you know, a nice safe address like 40,000 octal. And then let's put some things into the output buffer. So let's move 101, and let me make some labels up here. So console out is going to be that data register 177566. And console in will be 177562. And you may be noticing that, you know, when I was using these examine commands, I was using these much longer addresses, these 22-bit addresses, whereas here I'm using a 16-bit address. So PDP-11 is a 16-bit machine. All the addresses you specify have to fit in 16 bits, but there is a memory map that translates these into the actual locations it will go to in the physical memory, and that map is set up so that when I try to go to 177562, it'll actually go to 177.77562, which is the actual UNIBUS address where this console system is located. So this reads from the keyboard and writes to the printer. I got those backwards. Alright, so let's do some output. So let's just move a 101 into the console output location. And then we'll just go into an infinite loop. So it should just take the letter A and send it to our console output. So let's compile that and then load that and continue, and there's a letter A. If you missed it, I'll go ahead and reload it and look up here, and I'll say continue, and there's letter A. So so we can do this under program control. So let's try outputting more stuff. Let's output the letters A through E. And if I run that, well, all I get is the letter E. And I can try running this again, load A, and send it, and I'm just getting the letter E. And that's a little strange. So why would that be happening? Well, let's change the order around so that the last thing we try to output is the letter A. When we run that, we get the letter A. So it appears that only the last character is being sent, but what's actually happening is we are sending characters faster than the terminal can receive. So with the physical DL11, it might be, you know, a 1200 baud device. It could receive 120 characters per second. Certainly it's not going to be able to receive and print characters as fast as we can move from one of these instructions to the next, which would be a few microseconds. And these were, you know, large mechanical devices. They had to physically move a print head or physically scroll a sheet of paper and so on. So we're overflowing the buffer as we run these commands. And in fact, you know, we start trying to send a 101, but that gets overwritten by the 102, 3, 4, and after the 105, there's enough delay that actually gets sent out to the console. So this is where we need to look at these status registers. So let me go back to the DL11 section, and let's look at the transmit status register. And if we look at bit 7, which is right here, that's called transmitter ready, it says that this is cleared when we load something into the transmit buffer, and then when it's ready for another character, it sets that bit. So before we load something into the output buffer, let's check bit 7 of the status register and make sure that it's equal to a 1. So I'm going to put a few more symbols in here. So status out will be 564, and the input status will be 560. That's the receive status. So 560 receiver status register. And that's also going to depend on bit 7. So now I'm going to write a function down here. So wait for transmitter to be ready. So we'll do a write wait, and we'll test bit 200 is octal code for something with a 1 in bit 7. And we'll test status register output. And we want to see if that's set. So if it's equal to 0, then it's not set. And we'll wait some more. Otherwise we'll say good to go. And now after we send each of these, we're going to say wait. And we should probably do one before. So basically the same setup as before, except we wait for the transmitter to be ready, and then we load something into the output buffer. And this should send A through E. We'll compile that. We'll load A, we'll run it, and watch our output window up here. And there's our ABCDE. So this is the controlled way to do output, by checking the status register to make sure that that it's safe to send, that the transmitter has finished processing whatever it was working on before. So we can also work on the input side. So let's do let's make a read function. Let's read one character from the console. So we'll test bit 7 on the input register. See if there's a character ready. And if that bit is a 0, then there's no character ready. Otherwise, we'll go ahead and return, saying there is a character ready. And so we can change our code here. We'll wait for a character to arrive, and then we can move console in into R0. This is the character. We'll wait for it to be safe to write, and then we'll say move R0 console out, and then we'll go back and loop again. So read a character, stick it in R0, wait for the transmitter to be ready, move that character into C out, go back to loop, compile that. I messed up my symbols. It was console in and console out. Load that and continue, and now if I type ABC, I get an echo back. If I type XYZ, I get XYZ 1 2 3 4 5, and so on and so forth. So now we're reliably echoing input from the keyboard. So that's good. Let's do one more thing. Let's engage with the switches and the LEDs just to see if we can. So let me add a few more labels here. So the LEDs and the switches are at the same location. And let's just read the switches as an ASCII code and send whatever is in there to our console. So so wait till we can send, and then let's move switches into console output. And go back to the loop. So assemble that, load A, continue. Not seeing a lot happening yet. But let me go ahead and load in a value like 64 on my switches, and suddenly we're getting ASCII character 64, which is an @ sign. Here's 65 is an A, here's a C, here's a B. So we can read in from this this peripheral device, this front panel, and we can send to the simulated console. Now it's going a little nuts because it just keeps sending, and why is it doing that? Because that's exactly what we told it to do. Just as soon as you can take another character, take whatever's on the switches and send that out. So let's take advantage of our programming and do something a little more nuanced. Let's only have it transmit when let's say when a character changes. So move our switch into R4. So we'll remember the current switch value. And our loop, we're going to say let's compare switches to R4. So have our switches changed, and branch of it to equal loop. So if they haven't changed, we're just going to go back and just hang out in loop. Otherwise, we're going to save our current switch value in R4. We'll go ahead and wait till it's safe to send the character, and then we'll move our switches into console output, and we'll go back and loop again. And so this will do exactly the same thing we just did, except if our switches haven't changed, this should just sit in an infinite loop, and then when we flip any of these switches, it should send the new character. So let's go ahead and compile that, load it, and run, and you can see our output is nice and stable here. But if I flip a switch, now it displays whatever that ASCII character is, and each time I change a switch, it will go ahead and send the corresponding character. So there's a space, and here's some punctuation, and here's a number 3 and 2 and 0 and 1 and so on. So just an example of being able to with very few instructions interact with peripheral devices such as the console input and output. And any of this stuff that you want to dig into, this peripheral handbook is a good guide. It's got a bit of a summary of the main types of devices here, and you kind of have to know what you're looking for sometimes. But in this case, DL11s, those are down at page 128, and if you go down there, this tells you all about the DL11, including some high-level descriptions, baud rates, operation, how you hook it up, electrical characteristics, some of the details of how it does what it does, the transmit buffer, how that's wired up to the status bits and so on. And then there's a programming section that talks about how to use those registers. Now, we didn't play with interrupts, we'll talk about interrupts later, but interrupts are a way we could set it up to alert the CPU when something changes, like when a character arrives, and have it interrupt whatever the CPU is doing so we can go off and respond to that change in the peripheral. And for all these devices, there's usually a series of registers with a series of bits that describe how you interact with the device. And some of them are as straightforward as the console we just saw. Some of them, like the floppy disk controllers, get a lot more complex. But it's all basically the same drill. All right, so that was a basic example of input-output operations. If you wanted to work with a paper tape punch, paper tape reader, line printer, and so on, those are exactly the same deal. The difference is in the simulator, when we look at this, we can say show paper tape punch, and it will tell us the addresses it has in memory, the interrupt vector, where it looks for how to respond to an interrupt, but it also says not attached. And what we can do is we can say attach paper tape punch to testfile.txt, and it'll create a file called testfile.txt. And if I interact with these addresses in a way that would normally cause a character to be punched on this paper tape, it will instead get written into this file. And I can also attach the paper tape reader to a file, and then when I interact in a way that would ingest a character from the tape, it'll just read it from the file. So we can still work with these very old school devices, emulating their behavior and interacting with files. All right, that's what we got for video 5. I'll see you next time.